Good evening. Welcome to Lecture 2 of Topic 2 of Unit 3, Potential Difference. This video will be covering the main ideas of Chapter 7.3 and 7.4 of Book 1. You should complete this reading before class. Here are your learning intentions and success criteria. Please pause the video and attempt to complete the KS table down below. Alright, welcome back. So having a look here, we've got a couple of knowledge type verbs and a skills verb. They're popping up with the apply. So things that you should be asking yourself, what is electric potential difference and power? It's pretty hard to define them if you don't know what they are. Secondly, what are Kirchhoffs laws? Again, if you don't know what they are, you can't apply them. And then, well, what is charge separation? Because it's part of this explain, connecting this idea of potential difference that we had back up here and something else. And so our skills here is that apply. You need to be able to apply Kirchhoff's laws. What situations can we apply them in, and what does that look like? So, need to do a bit of drawing for this one. I want you to imagine a set of shelves. And you might have near them, and I want you to imagine that there's a cat. Now, can I draw a cat? That is the question. Ears, legs, tail, 2 whiskers. That's enough. That's a cat. And you've got a book here on the bottom shelf. But the cat decides wants to sleep there and pushes the book off. Of course, it's going to fall. It's going to hit the ground. We know from our studies in motion last year that objects get pulled down by gravity. And so if we want to lift them up to some point, we have to do some work. So we need to do some work. And you may recall the further you lift them, the more work you've got to do. So work is proportional to height. It's also proportional to mass. We know this. The bigger something is, that's a bad looking proportional sign. The bigger something is, the more you've got to work. But it's also proportional to gravity. If we lift it on the moon, it's a bit easier than if we lift it here on Earth. So you get your book, you go back, and you decide to put it up higher. Up there. The cat takes offense to this and decides to locate that location is where it must sleep, so it pushes the book off again, and so it falls to the ground. But now the sound is louder because there was more energy with it. There was more kinetic energy. Okay? Now this analogy is really good for electrical potential energy, except instead of a book, we're going to have a charge, like an electron. Instead of gravity, we're going to have an electric field. Okay? Now, an electric field is something that applies a force to anything with an electric charge. The same way gravity is something that applies a force to anything with mass. Okay? So all we're doing is, instead of talking about things with mass, we're talking about things with charge. If there's no charge, an electric field won't affect it. Same way something doesn't have mass, gravity shouldn't affect it. Though light certainly starts getting a bit weird with that, but let's not worry about relativity at this moment. Let's not ruin a perfectly good analogy. Now we're going to look at fields a lot deeper in electromagnetism in Unit 4. But all I need you to recall is that a field is something that causes a push or a pull. That's it. Now in my field, my charge, my book, my charged book, it wants to move to the source. It's attracted to it. And so if I want to keep it away from the source, I've got to put some work in it to move it away. I don't have to do any work to hold it. You might be screaming at me, but Mr. Warren, if I hold a book up, my arms get tired. What do you mean I'm not doing any work? That's biomechanical work. You're not doing any work against gravity for the book, you're doing work against gravity for yourself. But that book there, we're not putting any more energy into it to hold it up. That's our muscle fibers, contracting and expanding. The bigger the charge, which is basically the same as the bigger the book, the more work you've got to do. Okay, it's like if I put a small student, a grade 7 student, on a my rolly chair, the one in my lab, and I push them along the ground. That's a lot easier than if I get, say, a big Year 12 boy and I put him on the chair and I push him along the ground on the chair. It's going to take more work. So the bigger the charge, the more work you've got to do. The further you want it to go, the more work you've got to do. That one's a bit obvious. And there's an equation that represents this in electromagnetics, circuitry. Right? Work equals Q for charge, times E for the strength of the electric field and the distance you want to move it. Now, you don't need to remember this formula. It doesn't appear in your formula booklet, but the syllabus does require you to be able to explain why charge separation causes a potential difference. And we're going to get to how QW work relates to potential difference in a second, but here's the first part of it. So the bigger the charge, the bigger the field, right? And this field is related to the source charge, what the thing we're moving against, the same way that gravity's field is related to the source mass, planets for example. In D, that's the separation distance. Okay, good formula, remember, to explain the concept, but not something you've got to do any calculations with. So this energy that we're storing here, we call this electric potential energy. Okay? So this work that we've done to push our charges away from something else is called electric potential energy. Now you might go, but what if the charge is the same, is a different sign, the same sign to it? Wouldn't it want to go away on its own? In which case then we'd be doing work to bring them closer together, like when you do work to bring two north poles of a magnet close together. You can feel that work you've got to do. So what we've done here is called electric potential energy, and we're going to have some very similar names in a second, so you've got to keep a close track on this. If I divide the energy by the total amount of charge we've moved, we call this electric potential. So this is electric potential energy, but if I take this and I divide it by the Q, and you might see, hey wait, there's a Q in both, wouldn't they just cancel? Yes, that does work, but that's not a formula you need to be able to remember. This is called electric potential. This one you do need to remember, the work divided by the charge, and this is what we call voltage. If you look on the battery, you'll see a little measure of voltage on the side. That's what this is. Okay. Now, so far we've had two terms, and they're pretty similar. The naming kind of sucks in this. I do appreciate that it's kind of annoying, but it doesn't stop there. Because every point in space will have an electric potential from every possible charge, we will see the formula for the electric field and electric forces in electromagnetism in Unit 4, but basically it's proportional to inverse R squared, which means even if R gets really, really, really big, as in infinitely big, it's still never exactly zero. We can define anywhere as zero, but so for anything like more than a meter or so, it's basically zero, unless you're dealing with very, very big amounts of voltage. But otherwise, yeah, it does go on forever. Right? So every point in space has a electric potential from everything else. Right now, you sitting here on Earth, you've got an electric potential from some of the charged ions in the sun. Even though there's billions and billions of ions up there, lots of positives and negatives, we could work out, how much push and pull there actually is. And even if it was all positive ions or all negative ions, the total push or pull wouldn't be all that much, because we're very, very far away from that electric source. So the big thing we're going to look at is potential difference. Okay, so we're not going to worry about electric potential, but we do use that to work out potential difference. And what this is the difference in potentials between 2 points. Okay, nice and easy. Difference in the potential between 2 points. And what we're going to do is going to cheat and make one of the points equal to 0. So that makes the math nice and easy, that the potential difference, remember V was electric potential, so we could call this electric potential difference if you wanted to. Difference just means delta, change, final take initial. If we make either of them 0, then the potential difference is just going to be V. And if I draw this out, if I have some charge here, okay, plus Q, big charge, remember Q is for charge as well as for heat, and then we have some small little thing over here, maybe a proton, you'll also have a positive Q. Okay. At this distance, there is some strength of the electric field. There is also a distance between the two things, and so if I bring it a certain distance, okay, whoops, there will be a change in the voltage. If we say, let's just make that equal to 0, because that's where we started at, then all we care about is, well, what is this one going to be equal to, and that will give us our potential difference there. So sometimes we do cheat a little bit on the math just to make it easy for ourselves. The reason we do this for algebra is that it just gets rid of some of the annoyances. You don't have to when you do calculus for this though, because the integrals deal with some of this annoyance. But we're not doing calculus. So let's have a look at where this is actually important in a practical sense. Let's look at circuits, because that's what our topic is on. If we measure using a voltmeter around a simple circuit, here's a simple circuit, we've got a battery, we've got some sort of load, and it just loops back to the start, we get a graph like the one underneath it. Now we're going to ignore the loop backwards here, that doesn't matter. But what we can do is observe what's happening to the voltage along this stretch here, because over here nothing should happen to the voltage. It will in the real world, because wires do have a little bit of resistance, but in the make-believe world of physics calculations, where we try to make things easy on ourselves, we just pretend it doesn't. So we can see here, there is 0 voltage, gets to the battery, and then the voltage rises, goes up to 6 volts. Goes along, hits the load element, and a load element is just a fancy word for anything that's doing some work. A light bulb, a fan, a monitor, your headphones right now, or your speakers listening to my voice. All these things are load elements. And you can see here, drops back to 0. Now, if there'd been 2 load elements, the first one would not drop it all the way to 0, but the second one would drop it to 0. Okay. One of the things I was hoping you would observe with the FET simulation, or if this is 2022 or further on, will observe possibly, is that the potential difference, the voltage raised by the battery, okay, will equal the sum of the potentials lowered by the load elements on one loop. And this is Kirchhoff's voltage law, as the syllabus calls it. I prefer to call it Kirchhoff's loop law because it describes what we're talking about. Okay, so here's the voltage law. The sum of potential differences raised by batteries will equal the sum of potential differences lowered by load elements. Even that, I think I've sort of tried to make it a bit cleaner compared to what the syllabus and text write. Here's how I write it. The sum of voltages is equal to 0 on a closed loop. Here's a closed loop. I've started here, I've gone all the way around, I've got back to where I started from. That's a loop. This goes up, this goes down. That's it. If this goes up by 6, this is the only thing, this must go down by 6. If this was the battery, then there were 2, that would go down by something, that would go down by something, but the whole thing would equal 6. Here is something on a parallel circuit though. So if you've got more than one path loop, this one's got 3 as we can see, then each individual loop will sum to a 0 net potential difference. So this picture here we have 60 volts. And we're going to go from the positive side, the long side of the battery side. We get to here and we're going to split 3 ways. 1, 2, 3. So we'll deal with the current in a second. This one will go, say if we go this path, come back to here and then back around. I only went through one thing. There's my ammeter that doesn't take any voltage. Here's my only bit of resistance. Here's my load. So since that gave up 60 volts, that has to take 60 volts. And while we haven't done Ohm's law yet, I will just write it down. V equals IR. That has a resistance of 5 and a current of 12. Remember our last video we talked that the symbol for current is I, because old electrical French chemists hate us. 12 times 5 is equal to 60. Matches up. We get along to the second one. Here, goes through here, 6 amps of current. 10 ohms of resistance. 6 times 10 is 60. So this path is taking 60 volts. 4 times 15, 60. So this path is also taking 60 volts. So remember, here's one path. That's a closed loop. Yes, it doesn't go through those two. It doesn't need to. Okay. Kirchhoff's voltage laws say that any one closed loop, okay, will then allow us to know, well, what is the sum of voltages, and that will be 0. My second loop here, so there's my second loop and my third loop. Okay, a loop is just one closed path. Okay, let's have a quick pause for an activity. I've given you 3 terms: electric potential energy, electric potential, and potential difference. Now, all 3 of them are pretty similar, so it's easy to make mistakes. I want you to use the 3-way Venn diagram I've got down there to sort out similarities and differences. Formulas that connect the two would help you with some similarities, and differences, for example, would be more likely along the lines of definitions to show where they're separate from each other. Think about what do they explain, what units are they measured in. Go back and have a look through and see what you can fill in for it. Alright, hopefully you've given that a good shot. Let's continue on. So that was Kirchhoff's laws, and I just wanted to put the 2 laws in one place. In the previous video we discussed current, but we didn't talk about Kirchhoff's current law. I forgot the capital C. Kirchhoff's loop law, okay, as I like to call it. You'll probably hear me call it the loop law a lot, or the voltage law. Well, we just covered that one. The other is Kirchhoff's current law. I prefer to call it the junction law because it makes it a bit easier to think about what this actually is. Now, Kirchhoff's current law states the sum of currents flowing into a junction or a point will equal the sum of current flowing out of a junction or a point. They won't necessarily be equal to each other. Okay, and a couple of people mentioned that in emails from the FET simulation stuff that you guys did, because you didn't get to play around with the resistance on the different paths, so they're not going to be equal. It's just that the total in should equal the total out. And go try this with the FET simulation if you don't believe me. Here is one that I set up before. Let's have a talk through. Here's our positive terminal. You can see the little beep there. So that means the current is leaving here, and it is splitting into a fork, going through 2 bits, coming together, splitting again, okay, going through the 2 resistive loads, coming together, then back through the thing. So, here's our first junction. Here's the current coming in, and here's the current going out. Now, this 1.5 amps, this is saying for all of this section here, because it's all just one straight bit. Okay, so here it's 1.5, and if we see here, this bit is 1, this bit is 0.5. So 1, 0.5. 1.5 equals 1 plus 0.5. Junction law holds. Let's have a look at this bit over here. We've got 2 junctions coming together to make one junction. I will get rid of that one at the bottom just because it's a little bit harder to see with that driver. Okay, this one's 1.5 over here. We can see that from my ammeter I've placed here. This is 1.2, this is 0.3. 1.2 plus 0.3 equals 1.5. Junction law holds. Okay, what about this messy thing here? We have one junction here which is 1.2, one output here which is 0.3, and here we have an input of 1 and an input of 0.5. Well, 1 plus 0.5, 1.5, 1.2 plus 0.3, 1.5. The total current in equals the total current out. This is all Kirchhoff junction law says. As I've said though, the text in the syllabus calls it Kirchhoff's current laws. I like to think about the features that they're talking about because it makes it easy for you to see on diagrams, circuit diagrams, when we do some work with this, as well as applying it to situations. Now, that's what we're going to do on Kirchhoff's laws at the moment. We're going to come back to it when we revisit Chapter 9 after your data test, so a little bit later on when we do our student experiments. Alright, so the last bit of basic electrical circuits we need before we go into resistance is the idea of power. In all physics topics, regardless of whether it's heat, electricity, motion, radiation, anything at all, if you have some sort of energy or some sort of energy change and you divide it by the time it takes, that is power. Power is just the rate of energy being used. So for the stuff that we've just talked about here, power equals work over time. We had some stuff with work before in terms of voltage being a proportion of charge. Remember, work divided by charge equals voltage. So we can substitute that into there. It has the symbol P, as we can see there in the formula, and has the unit watts. Note the unit watts has the symbol W, but the power is watts divided by, or joules divided by time. So you've got to make sure that this W doesn't get confused for this W. And it also creates the best physics joke ever. You're a unit of power, Harry. I'm a what? Okay, you'll see me say that, or you hear me say that a lot. No, so 50 watts does not mean the work equals 50, unless time actually happens to be 1 second for the question that you're dealing with. Okay, and the first power equation we're going to use, there's at least one other one that we're going to use after we deal with resistance, is that power equals voltage, how hard you push, multiplied by the current, how fast it ends up going. Note some texts do have the V and the I swapped around. It doesn't matter which. There is a derivation for this in your textbook, but you don't have to be able to derive it, so don't worry about memorizing it unless you're really super keen. Okay, let's have a look at some examples. So here's our first one, 7.4a. Touch blurry, sorry. An electric heater has a power of 2 kW. K means kilo, remember, time. We're going to change that to our SI unit straight away. A, determine the power of the heater in watts. B, calculate how much energy the heater will use in 10 minutes. So, let's have a look at that. First thing is, what is the power in watts? So we're just going to convert kilowatts. So we have power equals 2 kilowatts. And really, this is something you should always do. If you have a number given to you in metric prefixes, kilo, mega, milli, anything like that, convert it straight away. Don't even start thinking about it until you've got it in a format that is actually usable for you. So 2 times 10 to the 3 watts. Or you could write it as 2000 if you prefer. But make it easy on yourself. Kilo equals times 10 to the 3. And guess what? That's given to you in your formula booklet. So you don't ever need to memorize it. You're just going to know, hey, I should convert this. Give it a shot. Calculate how much energy the heater will use in 10 minutes. So we've got 10 minutes there. So T equals 10 minutes. But that is not our SI unit. So that would be 600 seconds. 10 times 60. We know that power equals work over time, and work is just energy that's being done to something. So let's convert that. Work equals power times time equals 2 times 10 to the 3 times 600, and that will give us 1.2 times 10 to the 6 joules. 10 to the 6 is capital M for megajoules as well. I would accept either. Leaving it as times 10 to the 6 means that you don't have to worry about reading stuff off your calculator and then going, what do I convert this into? Scientific notation, perfectly fine. There are some extra power equations, as I said, but I don't think they come up in this topic. No. Okay, so second question here. Determine the flow of current in a toaster that has a power rating of 1200 watts and is connected to the 240 volt home supply. So now we have a power and we have a voltage, and we need to find a current. So we have a power, turn that into pen, power equals 1200, voltage equals 240, and we're trying to figure out I. As I said, P equals V times I. Let's rearrange that. P over V equals I. 1200 over 240 is going to equal 5 amps of current. Not too bad. Alright, and our last worked example, 7.4c, calculate how many joules of electrical energy are transferred per second by a 6 volt 0.5 amp lamp. Now, I don't like what the the text has done there, in that they go for this substituted formula straight away. It does actually derive it just above the worked example, but I'm going to do the deriving first. So this is what I do when I don't have a direct formula. This is how I would tackle these things. We're after how many joules of energy, so that's going to be my work equals dunno, because all my formulas here are dealing with it in work. We've got a 6 volt equals voltage, and it's got a current of 0.5. What we do know, and we're after heat get transferred per second, so T equals 1. That'll be nice and easy. Alright, we need to work out how to get to work, and from starting with these things here. One way to tackle it is to write down, well, what equations do we have that actually involve, what's what I'm looking for, these things. Okay? I have a formula that says, well, work equals power times time. I've rearranged the one that we had before, and I do have time, and I do want watts there. I do want work there, and I have that power equals current times voltage, PIV, and I have those, so I could substitute those together. Work equals IVT, and now I can substitute them all in. Work equals 6 times 0.5 times 1, which is going to equal 3 joules of energy. Now, whenever you have a formula, a situation like this, where you have something you're trying to arrive at and you don't quite have everything, find a formula with it in it. Okay, and then identify, well, look, I need that, I had that, but I didn't have that. What formula do I have that deals with this? I had PIV and I had those two things, so now we can substitute all of them together. That's really the core essence of any sort of physics math problem solving, where you just need to identify what formulas to link together, and the way to do it is you have to write these things out so that you can see it and give it a shot. Even if you've got the wrong formula, okay, at least go, well, this thing is about work, let's write that formula down. This one's about work, let's write that formula down. And write them down until you spot the one that will help you out. Okay. Alright, so that's the end of this topic. In this video we've gone through the following concepts of potential difference in power. We've described Kirchhoff's laws, and we've explained the cause of potential difference. Right? For your entrance slip to class, I'd like you to please complete questions 1 to 5 in chapter 7.3 and questions 1 to 4 in chapter 7.4, and copy these answers into the 3.2.2 space on eLearn. Thank you very much for your time. Have a great night.